Today's lesson is on finite geometric series. We just completed recently in 13.1 arithmetic sequences and geometric sequences, and in 13.2 we talked about the sums of arithmetic series or sequences. And today we're going to talk about finite geometric series, and we're also going to still use our calculator. We can still use the summation, the sigma notation, and use the formula on our calculator in order to find these. An example of a finite geometric series is an example of this type of problem. Let's say we have a bank balance of $2,000 that we put in an IRA that pays 6% interest compounded annually per year. Now, after 1 year has passed, then we don't have $2,000 in there anymore. We have 2,000 times 1.06 plus 2,000, 6% being what we've earned on that money. So this continues to accrue interest, and so then we can see that the formula down here at the bottom, that the bank balance will be 2,000 plus 2,000 times 1.06 plus 2,000 times 1.06 squared, etc. And we would just keep adding those to the n minus 1 power. This is what we call a geometric series. Very much like the arithmetic series previously, but now we're going to have a geometric method to solve these. So we have, instead of a linear equation, we have an exponential equation, which we include right here. That's our exponential equation. Remember, this is where summation starts, this is where it ends, and these are the numbers we put into our function that we create. Now, we can go through this series and talk about the sum, but the formula is the sum of a finite geometric series is a times 1 minus r to the n all over 1 minus r. And it works for all geometric series. A is our first term, r is our common ratio, and n is the number of years. And that will give us our sum. So here's an example using the formula. Find the amount of money in the bank after b of 6, which is after 6 years. So we're going to have b of 6 equals, and it's right here, 2,000 times 1.06 to the 6 minus 1 power. So we would just type that in. Okay. We would get, oops, sorry. I got to use the proper formula, don't I? It's right here. Sorry. 2,000, that's a, times 1 minus r to the n over 1 minus r. And we just type that in, and we would have $13,950.64. Remember, we're putting $2,000 in the bank every year. Then in year 26, if we continued to put $2,000 in at a time and we earned 6% interest, look how much money we'd have after 26 years. Quite a hefty little sum. You know, if you just took 26 times 2,000, that'd only be $52,000. But look how interest has accrued on the rest of that money that you've put in there. So that's just using this simple formula right here for a geometric series. Another way of putting it another way is the drug levels in the body. And in example 3, we basically, in the book, you're taking 20 milligrams of a prescription, let's say, and you have a half-life of 1 day, which means at the end of the day, you have 10 milligrams left in your body. Well, that's why you take 20 milligrams every day, to keep that level. So this is an injection, but it could just be a pill too that you take on a daily basis, like a heart medication or a blood pressure medication or something like that. So the formula remains the same. You just use the same formula. A, which is 20, we're taking 20 milligrams. Your ratio is a half, there and there, and we want to know how many we have after 10 days. We would still have this amount of milligrams in our body. So again, just using the formula of a finite geometric series. So our problem set, our final problem set of the year, is found on page 552, 1 through 13, 16, 17, 19, 21, and 24. Complete that and please work on your